My name is Acep from Engineering Department of PJB Indonesia. Today I'm going to present Flutter analysis of elastic steam turbine power plant through Transient Blade Row simulation. Flutter is one of the phenomena under the field of aeroelasticity, in which unstable dynamic aeroelasticity occurs in the form of oscillation or continuous vibration on structure as a product of the interaction between elastic, inertia, and aerodynamic force. This study was conducted at elastic steam turbine blade of Unit 2 at Tanjung Awar 350 MW coal-fired power plant, which is operated at 3000 RPM or 50 Hz. This study focused on the flutter of Tanjung Awar lasted blade, where last wire contributes to the harmonic deformation characteristic of the blade surface. To correctly modulate this characteristic study, GFD and a harmonic deformation analysis were conducted before the Transient Blade Row Fourier transformation method were utilized for the flutter analysis. This example of dangerous flutter phenomenon causing Tacoma bridge collapse. Methodology: value of aerodynamic are plotted in respect with the rotor blade position with the stator blade. Interblade phase angle or IBPA of minus 180 degrees indicates that the position in which rotor blades start to approach a stator blade, while in 180 degrees IBPA coincides with the position in which the rotor blade exits the next stator blade. If the blade has a positive damping value, the vibration that may occur from unstable dynamic aeroelasticity or flutter has low to none potential of happening. On contrary, a negative damping value indicates potential of flutter to occur. Methodology: start modeling, rotor positioning, steady GFD analysis resulting in steady pressure and temperature, harmonic finite element analysis resulting in blade deformation, vibration modes, and frequency. Transient Blade Row CFD analysis resulting in aerodynamic damping and well power density. Aeroelastic stability curve. So the final purpose is to find out aeroelastic stability curve. This is the model of steam turbine low pressure tandem compound, but for CFD analysis to reduce resource for in ANSYS, we just use a full stack 5-plate CFD model. This is CFD analysis setup. This is boundary condition, inlet pressure, outlet pressure, extraction 1, 2, and 3 for domain interface frozen rotor at the interface rotational span per domain. Rotational periodicity at the connection between stationary and moving domain. General connection at connection between stationary domain. From this steady GFD analysis, the results are pressure data of blade surface to be used in harmonic analysis and boundary data for transient blade row simulation. Methodology: to accommodate the need of transient blade row analysis with Fourier transformation method, a null lofted fluid volume model was used. Rotor position last blade. The 79.17 mm line represents the distance between stator 7. So this is in terms of angle from the shaft axis, the distance between stator 7 is 360 degrees divided by number of blades, which is 68, and the result is 5.29. Our first rotor position in IBPA definition can be calculated. So this is how we calculate 56.74 divided 79.17 multiply 360 degrees minus 180 degrees equal to approximately 77 degrees. So for harmonic analysis, there are 3 RPM via analysis, or in a frequency, in terms of frequency, 50 Hertz, there are normal operation frequency or equal 3000 RPM, 150 Hertz and 250 Hertz. The maximum principal stress in MPA, the location is around less wire width area, in the middle of less wire. So we choose 150 because this maximum principal stress is around less wire width area, which is here. Evaluating the maximum deformation, X, Y, and Z direction for 2 plates at 150 Hertz vibration. This is for Transient Blade Row CFD analysis step. So for model Fourier transformation sampling plane between 2 phases, phase angle multiplier or PAM, or nodal for diameter multiplier of integer of number of blades divided by PAM equal to 30. Time period 0.02 second, and number of period per run 10 period or 2400 time step. So the rotational offset setting in ANSYS CFX that have to be filled with other IBPA value after being normalized with a stator 7 pitch or 360 degrees divided by 60x equal 5.29, as we explained before. This is the data point that we are evaluated in this study. IBPA is minus 70 degrees, 0, 77, and 180 degrees. So the rotational offset setting minus 2.16, minus 1.13, and 0, and 1.51. So this is how we do validation for CFD model. To the spirit calculation of turbine power from the actual operating data, which is 146 megawatt, and this is from CFD calculation 152 megawatt. So the difference is 4.1%. So this is, as we explained before, simulation result of flutter analysis is at a cumulative time step of 2400 or 10 period. So convergent trend for almost momentum, heat transfer, turbulence, also well, and boundary scale RMS parameter. Red graphs show aerodynamic damping 1 or correspond to the main plate that was under study, and green graphs show aerodynamic damping 2, which correspond to the second passage that was constructed to utilize the Transient Blade Row with a Fourier transforms model. So this is aerodynamic damping simulation at 77 degrees. This is 180 degrees. This is for 0 degrees. This is for minus 70 degrees. So we are plotted here for IBPA. minus 180 degrees, we got a positive value, or on minus 70 degrees we got a positive value, or we got a positive value. Therefore, we can conclude that the potential flutter is known to happening. The most positive wall power density value coincides with the position of last wire here. This confirms the design of elastic blade, especially the last wire placement, due to the characteristic of slender last blade rotor blade. Due to the characteristic of the slender elastic rotor blade, largest deformation will occur at the location without support and extend more outward radially, hence the placement of the last wire. Conclusion: based on the result from Transient Blade Row CFD analysis on elastic steam turbine blade of Unit 2 at Tanjung Awa 350 MW coal-fired power plant, IBPA position minus 180, minus 70, 0, 77, and 180 all have a positive value aerodynamic damping. Therefore, non-potential of flutter to occur. The potential of vibration from flutter to occur is low to none. Furthermore, of all mentioned IBPA position, so that the area with the most positive well power density value is around lashing wire location at the pressure side of blade surface. The well power density trends confirm the design of lash wire placement to minimize the high risk of deformation due to structural characteristic of the slender last blade profile.